Hello, algebra students. We're going to be working on section 4 for today on scatter plots. So let me share my screen and get the presentation going. So you will need a piece of paper for today's warm-up. So wait for it to load here. All right, you are asked to write an equation in point slope form for the line that passes through the points 1994, 369 and 1997, 456. All right, so take a minute, grab a calculator, and give that problem a try. All right, welcome back. Let's go ahead and check your work here. Grab my pen. Maybe, there we go. And so the first thing we need to do is find the slope. So I'm going to use 456 as my y2. So I have 456 minus 369 over 1997 minus 1994. All right, so 456 minus 369, grabbing the calculator, is 87 divided by 1997 minus 1994 would be 3, and 87 divided by 3 is 29. So that's our slope. And then we have to write an equation in point slope form. So we can use either pair of coordinates. I can either write this as y minus 369 equals 29 times the quantity x minus 1994. I could use that ordered pair for my point slope form, or you may have chosen to use the second ordered pair, so you'd have y minus 456 equals same slope 29 times the quantity x minus 1997. All right, again, those are both point slope form. If you wanted to change it to slope intercept form, you would use the distributive property. So let's go ahead and continue the presentation. You have some vocabulary to write down. It's a little bit different than what is in the book. So scatter plot is on page 113, but you will see the word line of fit on page 113, and I want you to cross off the words line of fit and replace it with the words best fit line. So go ahead and pause the video and copy both of those vocabulary terms into your journal. All right, welcome back. Let's continue the presentation. So we have here some examples of some scatter plots, and scatter plots just relate to quantities. So here we have Old Faithful eruptions, and we have the eruption time in minutes versus the time between the two eruptions. It's kind of an interesting little piece of data. Here you look at the daily temperature and how the visitors to a beach might increase or decrease, right? As it gets hotter, it looks like more people are going to the beach. This is one for a scatter plot of miles per gallon versus the weight of a vehicle. So you can see the heavier the vehicle is, the lower the miles per gallon that the car gets. And that makes sense, like big trucks aren't getting very good miles per gallon, whereas some little car, motorcycle, or whatever is going to get excellent gas mileage way up here because they don't weigh very much. All right, and that's what scatter plots are talking about. You need to add this to the vocabulary on page 113. Where the word correlation appears on page 113, you can change that to say correlation coefficient and write down this definition. All right, in the space at the bottom of the page, I would like you to do your best to kind of draw these little sample representations of correlation coefficients and what it might look like in terms of a graph. So you have a lot of empty space there in the bottom of 113. So copy these down. They don't have to be exact. If you'll notice, remember it says the value R of the correlation coefficient varies between -1 and 1, where -1 is a very strong negative correlation and +1 is a very strong positive correlation. So this would mean as one increases, the other increases. This would mean as one term increases, the other decreases, or vice versa. So this example here shows a correlation coefficient of a negative 0.9. So it's almost a -1. You can look, it's almost in a straight line, pretty close. Here's a negative 0.5. So it looks like as one increases, the other decreases. It's not particularly strong, right? These points are kind of all over. Here's a correlation showing a correlation really essentially 0, right? Where there's no line, you know, we can't tell what's going on with this one. Here's a positive correlation, not a very strong one. We're at 0.5, so kind of in the middle, but we can see there is somewhat some correlation. When we get to a positive 0.9, you can see it's getting stronger. It's nearly linear. And a correlation of 1 will be just like this, where it's right in a straight line. All right, let's look at extra practice on page 114. You have this graph, you have a scatter plot, and you're asked some questions about it. So it says, what was the weight of the baby at 4 months old? So let me grab my pen and we will do that again here. Pen color, let's go with blue here. What was the weight of the baby at 4 months old? So I go to 4 months on the graph. On the horizontal axis, I read up till I get to this point, go across to my vertical axis, and it looks like at 4 months old, the baby's weight was 14 pounds. The next question says, what was the age of the baby when its weight was 17.2 pounds? So I need to find 17.2. So that's in here somewhere. Looks like right about there would be 17.2 pounds. And if I go down and find the age for that, it would correspond to an age of 8 months. Then part C just asks a general question. What tends to happen to the weight of the baby as age increases? If we look, we can see this is going nearly in a straight line. We can say that the weight increases. And that makes sense, right? As a baby gets older, its weight is going to increase according to its age. All right. So on the next part, this is questions 2 through 4. The question says, tell whether X and Y show a positive, a negative, or no correlation. So if I look at question number 2 here, and I need to grab a pen. If I look at question 2, I can see it kind of somewhat upward trend. It's not particularly strong, but it does look like it has a positive correlation. It is increasing. As my X values increase, so do my Y values. So that looks like a positive correlation. Let's look at number 3. Here we can see it's going downhill. This looks like a negative correlation. Let's see, number 4. These points are all over the place. I would say there is no correlation here. Right, there's really nothing going on. As one thing increases, we can't tell what the other one's going to do. And number 5, again, this is going uphill. This looks like a positive correlation. All right, let's take a gander at the next slide. All right, this time it says, write an equation that models the depth of the water as a function of time. So I can look here and it looks like I have a y-intercept, right? So I need some points here for a slope. In general, you could plot these points and find ones that are really close. I'm just going to pick a, let's see if I can find some that'll come out nice here. Yeah, I'm going to use this ordered pair and this ordered pair. If you graph them, you can usually find ones that are pretty closely related, but I'm going to go ahead and use that pair of points. And I need to write an equation. So the first thing I'm going to do is find my slope. Notice these numbers here are my y values. So I'm going to write 17 minus 11, so the difference in the y values, over the difference in the x values. So 17 minus 11 is 6, 8 minus 4 is 4. So it looks like we have a slope of 3/2. So it looks like things are increasing. I could use one of these points, one of these points I just had and write in point slope form if I wanted. So y minus 11 equals 3/2 times the quantity x minus 4. All right, I could have also chosen to use my y-intercept here, take my slope. Remember, this is my slope, and I could have written y equals 3/2 x plus 6. So when you are writing an equation to model the data, it could be off a little bit depending on which points you pick, which ordered pairs you pick. That's why it's helpful to graph them and see 2 points that really are very representative of the function, and I just picked these two. Let's see how close this is to this equation. If I distribute, I get y minus 11 equals 3/2 x, and 3/2 times 4 would be -6. And then I'd add 11. And so using point slope with those two ordered pairs, I got y equals 3/2 x plus 5. Here I have y equals 3/2 x plus 6. So those are very close. Their y-intercepts are slightly off, same slope, right? It says to interpret the slope in the y-intercept of the line. So let's talk about this, and it doesn't matter which one we're talking about. Let's just look at this one. All right, and what the problem was about. So the problem says, the table shows the depth in centimeters of water filling a bathtub after t equals x minutes, after our time is x minutes. So our slope would be the tub, and this is our interpretation here, the tub fills at a rate, I don't know why this is writing so weird, at a rate of 3 centimeters, because it's going in centimeters, every 2 minutes. Hope you can read that. I don't know why it's being so choppy. All right, it fills 3 centimeters every 2 minutes. That's what that slope means. The y-intercept represents how much water was in the tub to start with. Oh, that's really nice. The depth of the water. Ay, ay, ay. The depth of the water at the start. Okay, sorry about the really bad writing. So if you can't read that, the y-intercept is the depth of the water at the start was 6 centimeters. That's what that means. All right, let's look at our next one. The next one is just the assignment. You have problems 1 through 12 on page 199. The links for this is in Schoology. If you have any questions, just send me an email. All right, good luck.